So this is a chapter on rotational motion and angular momentum. A couple of chapters ago we talked about uniform circular motion, and in it we defined angular velocity, and that's just the rate of change of angular position, and we used the variable omega, and we said the average angular velocity was the change in angle over the change in time. And we developed a few relationships like the speed of the edge of a wheel, that has radius r and angular velocity omega, has tangential velocity v equals omega times r. We sort of derived this, and we said, look, here's my wheel, it's traveling at omega, that's its angular velocity. It's got a radius r, and so if you were sitting here on the wheel, your velocity here, v, is just the arc length, if that's delta theta. This piece here is delta s, right? This arc length is just delta s, delta s over delta t. But from the definition of the arc length, that's just equal to delta theta times r over delta t, which is omega times r, because delta theta over delta t is omega. And so if you want to know the velocity you're traveling at the edge, you just multiply the angular velocity by r, and that gives you what we call the tangential velocity. So those are a couple of relationships we had. Omega average is the change in angle with respect to the change in time. And then we said v is equal to omega times r. We want to define an angular acceleration, and so we use the letter alpha, and that's equal to the change in angular velocity over the change in time. So this is the rate at which something is speeding up or slowing down, right? If the angular velocity is constant, which it was in the chapter we did on uniform circular motion, we have no angular acceleration because delta omega is 0. The angular velocity is constant. But if the thing is speeding up, like you turn on a fan and it starts to spin, or you step on the brakes on your car and your wheels come to a stop, right, then you do have an angular acceleration, and that's how you calculate it. And so here's an example. Suppose a wheel is spun from rest to 250 RPM in 5 seconds, right? So A, calculate the angular acceleration in radians per second squared, right? You can kind of tell that angular acceleration is going to be in radians per second because angular velocity is in radians per second, and then I'm dividing by seconds. So the first thing we need to do is get the is recognize that this is omega naught and this is omega final, and so delta omega is equal to omega minus omega naught, right? And that's 250 revolutions per minute, right? But I want to convert this into radians per second because that's what I'm going to be working with. And so I'm going to multiply this by 1 minute over 60 seconds, and by, I want to convert revolutions to radians, 2 pi radians per revolution, and I should be careful to cancel them to make sure I got the things in the denominator and the numerator correctly. And this comes out to about 26.2 radians per second, right? And so my angular acceleration, which is delta omega over delta t, is 26.2 radians per second over 5 seconds, which is like 5.24 radians per second squared. Right. So that's a simple use of this equation. Let me do a part B. So you've seen that. So in part B, in part B, the wheel is stopped with an angular acceleration of minus 87.3 radians per second squared, right? So it's spinning along. I think we had its angular velocity was omega final, once it was spinning up, was 26.2 radians per second. In the course of solving part A, that's what we got. We converted this, right? And now I'm going to break it to a stop, right? And so alpha is equal to delta omega over delta t. And so in part B, omega naught is equal to 26.2 radians per second, and omega final is equal to 0, right? Because it's now in part B, it's spinning, and we stop it, right? And so it starts out at 26.2 and it ends at 0. And so, but we're looking for the time. We know the angular acceleration, and so I'm going to rearrange this equation. I'm going to say delta t is equal to delta omega over alpha, right? I multiply both sides by delta t, divide both sides by alpha, and I get this. And so this becomes 26.2, omega minus omega final minus omega initial, so it's 0 minus 26.2 radians per second over my angular acceleration, which is minus 87.3 radians per second squared. And I get 0.30 seconds. So that's using the angular acceleration equation to solve some sort of, I would call these kinematics problems with rotation, right? And kinematics problems were velocity, position, velocity, and acceleration for straight lines, but now we're doing it for rotation. We're doing kinematics equations for rotation. So let's talk a little bit about tangential acceleration. So, we're talking about angular acceleration, right? But that's for the angle. The tangential acceleration is like, what's your meters per second squared going around this clover leaf? How fast is your car accelerating as you go around, right? And so we've already said that the tangential velocity, we just did this a screen ago, and in the uniform circular motion problem, we said, look, V tangential is equal to omega times r. And we got that from saying the tangential velocity was the arc length, the arc length, delta s, right? Delta s is just, it goes from, it covers that angle delta theta. This arc length is delta s over here, and it does it in time delta t. And so its tangential velocity is delta s over delta t. This would be a really small angle, right? A really tiny time, so that this curved line is almost straight. And then the delta s, just from the definition of radians, is delta theta times r over delta t, which is just omega times r, because delta theta delta t is omega, right? And so So now we want to calculate, so that was the tangential velocity, say. Now we want to calculate what the tangential acceleration is, and so we can calculate that one as well. This is just how fast is this car accelerating if he's stepping on the gas, as he's going around the curve, right? And so the tangential acceleration is just the change in the tangential velocity over the change in time. It's how fast your car is accelerating going up this thing, right? And so that's equal to the tangential velocity is just the change in omega r over the change in time. But r doesn't change. If it's a circle, r doesn't change. And so it's just delta omega over delta t times r. But that's just equal to alpha times r, right? Because we just said delta omega delta t is alpha. And so the tangential acceleration is alpha r, just like the tangential velocity is omega times r. So this is a problem on angular and tangential acceleration. This is just another example. A motorcycle can accelerate from 0 to 30 meters per second in 4.2 seconds. What's the angular acceleration of its 0.32 meter radius wheels? I am not going to do a good job of this. Yep, I was right. Okay. I don't know, it's got a motor there, it's got a gas tank here, it's got some handlebars coming up here, here's a person standing on something. I don't know why they're looking at you when they should be looking forward, but there it is. So the acceleration, it goes this way. These guys have an angular acceleration this way. And so there are a couple of things we should notice, right? The tangential velocity, that is, say, the velocity of the edge of the wheel, is going to be exactly the velocity of the motorcycle, right? Because the motorcycle, the wheel is at rest when it's in contact with the ground. And so however fast the rim of the wheel is spinning is how fast the ground is going by this way. So it's how fast the motorcycle is going that way. And so the forward direction is v tangential, and the acceleration in the forward direction is a tangential. And so this tells us that a tangential is equal to v minus v naught over delta t, right? Let me just write it this way. It's the change in velocity over the change in time, and that's equal to v tangential minus v naught tangential over delta t. And that's 30 meters per second minus 0 over 4.2 seconds. Right? And that's equal to about 7.14 meters per second squared. That's a tangential, right? And that's equal to alpha r, right? And so if I want alpha is equal to a tangential over r. You follow that? A tangential is equal to alpha r. Alpha is equal to a tangential over r. That's just 7.4 meters per second. Sorry, 7.14 meters per second squared over 0.32 seconds, which comes out to be 22.3 radians per second squared. Notice, as I've said a few times, seconds. Notice I've said a few times that I'm free to stick in 0.23 meters. I'm on it now. Radians per second squared. I think I've got it now. So this is the acceleration, 7.41 meters per second squared over 0.32 meters, right? This is the radius of the wheel. That's the acceleration of the vehicle that we calculated up here. I cancel the meters. I get 1 over second squared But I know this comes out in radians, and so since radians are not a unit, right? Radians is arc length over radius, which is meters over meters, which is not a unit. I'm free to stick it in wherever I need it. And so there's my radians per second squared, and I get, when I divide those two, I get 22.3.